we're going to look at a bunch of different examples here of finding limits. So I want to point out in the instructions that it specifically says to use theorems to find each limit and to be sure to state which theorems you're using and show work thoroughly to justify each part of the use of the theorems. So part of what I want to do in this problem is talk about getting answers, but part of what I want to do in this video is also talk about what you should be writing to demonstrate that you're showing that work thoroughly and justifying the use of the different theorems. All right, so I'm going to move over here where I have listed all of the limit theorems that we have so far. And it's more than will fit on this screen, but these are ones that we've gone over so far in some previous videos. A couple of specific functions, kind of as basic building blocks, the identity and the constant function, and then a bunch of theorems about combining functions, which then allows you to get some theorems about polynomials and rational functions. We have another theorem here about transcendental functions, so trig functions, exponential functions, logarithm function as some examples of transcendental functions. And then a few other theorems here, functions that agree at all but one point, and sandwich theorem. So one thing that's kind of difficult about these mixed examples is knowing where to start. So I'm just going to write out here to the side a couple of hints about kind of how to think that through and just how I think through what theorem to use. So the first thing I try to think about is if I can use a substitution shortcut theorem of some kind. So I'm really thinking about whether I would be able to substitute the value in, even though that's not really what the limit is asking about, whether that's something that could work for the problem. If that's not something that could work for the problem that I'm working on, then I might think about doing some sort of simplification to rewrite the function in a simpler form, and then perhaps use a substitution shortcut theorem. Often, when you're doing that, you're really using the theorem about functions that agree at all but one point. So you're thinking about rewriting the function, maybe doing some cancellation, so you technically end up with a different function, and so you're really using the theorem about functions that agree at all but one point, and then maybe in combination with a substitution shortcut theorem. Generally, I think through whether any of those strategies would work first, and if not, then I might think about using sandwich theorem. Sandwich theorem can be a little bit more difficult because you have to think about what functions to use to sandwich the function you're working on, and sometimes that can be kind of difficult. So I usually only attempt to use that if some of my other strategies are not going to work. All right, so let's just go through these examples here. So for this first one, limit as x approaches 1 of the natural logarithm of x. And so we actually have a theorem that directly talks about the natural logarithm function. It's one of our substitution shortcut theorems for transcendental functions. So it says that as long as x equals c is in the domain of the function, then the limit as x approaches c of the natural log function is just natural log of c. And so the domain of the natural logarithm function is 0 to infinity, which means that we are in luck when we are approaching x equals 1. So we can actually just use that substitution shortcut theorem. And I'm just going to label that here. It's the substitution shortcut theorem, and it's the part that's about transcendental functions. And so I'm going to use that, and I'm going to just substitute in 1, and then I'm going to evaluate natural logarithm of 1, which is 0. Okay, so the next one here, I'm going to again think about whether I can use a substitution shortcut theorem. And so if I just had 5 minus x without the radical there, I would be able to just use a substitution shortcut theorem for a polynomial. 5 minus x is a polynomial. But the square root of 5 minus x is not a polynomial. So because I have that radical there, I'm actually going to have to use a couple of theorems in combination. I can use substitution shortcut theorems here. So I'm going to be able to just substitute in 3. And so I get square root of 5 minus 3, which is square root of 2. Notice that that is a value I would not really be able to get from just using a table or a graph. but square root of 2 is the value for this limit, and so I'm technically using two different theorems here. I'm using a substitution shortcut theorem for the polynomials, and then the other theorem that I'm using, I would notice that the square root can be written as a 1/2 power. So I can think about that as 5 minus x to the 1/2 power. And we have a combining functions theorem that is about powers. So let me just scroll over here to look at that. Power rule for combining functions says that provided I know the limit of the inner function, which is a polynomial, so we can use substitution shortcut theorem for that, then I can get the limit is just the limit of that inner function to whatever power, to the r over s power, provided r and s are integers. So that's the other part of what we're using here. So combining functions theorem, and it's really the power rule for that. So I'm really using two different theorems here for this. So really you should state both of those. And notice I've abbreviated those. You don't need to write out the whole thing in words, just indication that you know what theorems that you're using. All right, on this next one, I have a rational function. I have a polynomial on the numerator and a polynomial on the denominator. So I do have a substitution shortcut theorem for rational functions, but notice that that theorem talks about that the denominator should not be 0 when you substitute in x equals 0. And so that does not work here. I cannot just do a substitution shortcut theorem. So remember when I talked about sort of my little mental checklist, I often think about, can I do this? If you cannot substitute in, that doesn't mean you can't find the limit or that the limit doesn't exist. It just means that you might need to try one of the other strategies to figure out what that limit is. So this is one that you might notice on the numerator. If you do a little bit of algebra on the numerator, you're going to be able to get some simplification. So let's go ahead and try to do that, simplifying the numerator, and see what happens. So if I expand out the 5 plus x, the quantity squared, I'll have 25 plus 10x plus x squared. And then I also have the minus 25 term on the numerator, and that's convenient because that allows some cancellation. My 25s cancel. And then I still cannot use a substitution shortcut because I cannot substitute in x equals 0. So at this point I really haven't used any theorems. I've just sort of rewritten the function that I have. But the next thing that you might notice is that you can factor an x out of the numerator. And then you'll be able to cancel that with the x in the denominator. So at the instant when you do that cancellation, you really have a different function than the one you started with. The original function has a domain that is all real numbers except 0. And this new function that I have here has a domain that is all real numbers including 0. So they're not the same function, but they do have the same limit. So at this step, where I rewrote the function without the x on the denominator, I used the theorem about functions that agree at all but one point. So that's the abbreviation I usually use for that theorem, functions that agree at all but one point. And the nice thing about what I have left is just a polynomial function, 10 plus x. So I can just go ahead and do substitution now. So 10 plus 0, and I get 10 for my answer. So I used functions that agree at all but one point when I did the cancellation. And then here at the end, when I went ahead and substituted in, I used the substitution shortcut theorem for polynomials. All right, so these two things that I've written here in pink on this problem are indicating what theorem I used and which step I used it in. And then all the other work, the algebra of expanding out and canceling and substituting in, all that other algebra is showing the work to justify the use of those theorems. All right, let's look at this next example here. Again, I have a rational function. I actually have a rational function within a rational function here. You might start by thinking about, can you just substitute in x equals 0? And you should pretty quickly say, no, you cannot, because that would make the denominator 0. So that does not necessarily mean that the limit does not exist. It just means I can't start by using a substitution shortcut theorem. I have to do something else. All right, so what I would notice here is that I've got fractions within fractions, and so I can do some algebra to simplify that. this tends to be algebra that students might have forgotten a little bit. So there are a couple different ways that you could handle the algebra here, and any of those are fine as long as you do the algebra correctly. So I'm just going to mention a couple different ways, but I'm just going to do the problem one way. So one possible method is to find a common denominator for these two sort of mini fractions that are in the larger fraction here. If I find a common denominator for those two, and then treat the problem as a division problem. So I have that numerator fraction that I get when I find a common denominator there, and then I have that whole thing divided by x. So you can do the problem that way and simplify, simplify, simplify. Another way that you can do this is to handle this by multiplying both the numerator and denominator by something that will clear the fractions that are within the larger fraction. So I'm going to do this problem that way because it's a little bit more direct route to the answer. I don't care which way you do these problems as long as your algebra is correct. All right, so I'm going to look at the little fractions that are within the larger overall fraction. I'm going to think about what is the common denominator for those fractions. Right, so when you think about common denominators, you have to think about multiplication here, where you could multiply a denominator by so that they would have the same denominator. So the common denominator is 3 times x plus 3, not just x plus 3, but 3 times x plus 3, those two factors. So that's the common denominator of those two fractions that are on the numerator. So I'm going to multiply the numerator of this function by 3 times x plus 3, but I can't just go around multiplying numerators by things and have it still be the same expression. So I also have to multiply the denominator by that. If you want to look up some algebra review videos on this, this is called simplifying complex fractions, fractions within fractions, and this is one way to do that. So I multiplied through by the common denominator. What happens when I do that on the numerator, when I multiply 3 times x plus 3 to that first fraction on the numerator, I will have the x plus 3's will cancel, and so I will just be left with 3. So when I take this 3 times the quantity x plus 3 and I multiply it times the 1 over x plus 3's, the x plus 3's will cancel, and I'll just be left with 1 times 3, so just 3. And then when I multiply to the second term on the numerator, I'll circle that in a different color here. When I multiply the 3 times x plus 3 to the second fraction here on the numerator, the 3's will cancel. And so then I'll be left with x plus 3. I do have to be a little bit careful because I have this minus sign here that's going to apply to that entire x plus 3. So you can go ahead and distribute through the minus sign, or I'm going to just go ahead and write the parentheses here and distribute through in a later step. But the whole point of doing what I did on the numerator there was to clear the fractions that are within the larger fraction. On the denominator, don't forget you're also going to have to multiply the denominator of the overall fraction by the same thing. And I don't have anything that cancels there, so I'm left with x times 3 times x plus 3, or I might write that as 3x times x plus 3. Okay, one thing that I want to mention, and is true on the previous problem as well, notice that I have this LIM still written out front. That's not going away. That should be there in every step until you actually use those substitution shortcut theorems or whatever you're using to evaluate that limit. So that's one of those things about writing your work out correctly that sometimes students forget about at first, but you want to make sure you look back at your problem. If you didn't write that to start with, go fill that back in as you're finishing up with that. Okay, I might at this point still think about, can I do a substitution shortcut? And I cannot, because I can't put in x equals 0, because that would make the denominator 0. So I'm going to continue simplifying. On the numerator, when I distribute through the subtraction sign, I will get some nice simplification here. My 3's will cancel. And then I'll actually be able to do some cancellation that will give me a new function with a different domain that actually does allow me to finish by using a substitution shortcut. All right, so the next thing here, I will have a factor of x on the denominator and a factor of x on the numerator that will cancel. So I'll just be left with minus 1 on the numerator. And at the step where I did that cancellation is where I used that theorem about functions that agree at all but one point. At that step where I did the cancellation, where I changed the domain of the function I'm working with. It's not really the same function anymore. It agrees at all but one point. All right, but that is helpful because now I am to a place where I have a rational function whose domain does include x equals 0. So I can finish this problem by just substituting in x equals 0. And so I'm using a substitution shortcut theorem to finish this one here. So I get negative 1 over 3 times 3 is 9. So negative 1/9. And let me label where I used that other theorem here. So this step, I use the substitution shortcut theorem for rational functions. Notice that often when you use that theorem about functions that agree at all but one point, you're also using another theorem in combination with that to sort of finish the problem. Okay, let's look at these last two. Example 15 here is another one where I might like to try to start by substituting in x equals 0. I can't do that though, but I can do some simplification and then use hopefully a theorem about functions that agree at all but one point. So what can be difficult with this is knowing what simplification to do. And every problem is a little bit different, so you just have to kind of think through, well, what do I see that I could do to rewrite this one? So one thing that I notice here is that I have two fractions. They both have an x on the denominator and they're subtracted. So one thing that you might try is get a common denominator and combine these two fractions and see where that leads us. All right, so when I combine those two fractions, I'm not really using a theorem, I'm just doing some algebra. The common denominator is x times the square root of 1 plus x. So I'm going to go ahead and multiply this second fraction by square root of 1 plus x on numerator and square root of 1 plus x on denominator, and then combine them. So I will have 1 from the first fraction minus 1 times the square root of 1 plus x. So I'll write that like that. And then my common denominator, x times square root of 1 plus x. All right, I still cannot use a substitution shortcut. I cannot put in x equals 0 because it's not in the domain of this function. And so I might think about what other simplification I can do. It's tempting for students to cross out those square root of 1 plus x's, but algebra doesn't work that way. The square root of 1 plus x on the denominator is okay to cancel because it's a factor of the denominator. But on the numerator, it is not a factor of the numerator. That's subtraction there, so you can't just cancel those. What I can do, and we did in a previous video though, is you can think about rationalizing the numerator. It can be hard to know whether that's really going to work or help, but it's really the only thing that you kind of see to simplify this problem, and so it's worth a try to see if that helps. All right, so to rationalize the numerator, I'm going to multiply by what would be the other factor in the difference of squares. So 1 plus square root 1 plus x on the numerator, and then I'm also going to multiply that by that on the denominator. And the hope is that this helps. All right, so when I FOIL that out on the numerator, I will have the 1 times the 1, which just gives us 1 on the numerator. And then I will have the 1 times the square root of 1 plus x. So that'll give us plus 1 times square root of 1 plus x, or just plus square root of 1 plus x. And then the second term in the first factor, I'll have minus square root of 1 plus x times 1. And this should happen every time you're rationalizing. If you've multiplied by the correct thing, these middle terms should cancel out, so you don't necessarily need to write those if you know that's going to happen. And then the last term, the square root of 1 plus x times the square root of 1 plus x, that will just be 1 plus x. I do have to be a little careful because I'm going to have a minus out front of that though, so I'll have minus the quantity 1 plus x, and we'll need to distribute that minus sign through. All right, on the denominator of the fraction, I'm not going to multiply these things out. You could do that, but you'll probably end up wanting to refactor if you do. Sometimes the more of these problems you do, the more you can see a step or two ahead and sort of know what's going to happen, so you know whether to multiply things out or not. So rationalizing, the whole point is that you have this difference of squares and these middle terms cancel. So you should expect that that's going to happen where you have these two middle terms that canceled. Then I have 1 minus 1, and then I'll need to distribute this minus sign through here as well. I'm going to go ahead and write out another step, but it's okay with me if you skip a little bit of algebra here, as long as you don't skip all the algebra. So on the numerator, my 1 minus 1 cancel, and I'm left with just negative x on the numerator. And then when I have that negative x on the numerator, I can think about that as negative 1 times x, and I'm able to cancel that x with an x on the denominator, and I'm just left with negative 1 on the numerator then. All right, so at that point where I changed the domain of the function, that's where I used the theorem about functions that agree at all but one point. So I've indicated that they're in pink, where I wrote functions that agree at all but one point, my little abbreviation for that. And looks like a big mess here, but one thing that you might notice is that at this point x equals 0 is in the domain of what I have here, so I can go ahead and use a substitution shortcut theorem to finish this problem and just substitute in x equals 0, remembering that that is not really what limits are about. But when I can use the substitution shortcut theorem, it makes everything nice and easy. All right, so the numerator is negative 1. On the denominator, I have square root of 1 plus 0 is square root of 1, which is just 1 times, and then in the parentheses 1 plus 1, which is 2. So I end up with negative 1/2 for my answer here. This is one where we did enough steps here. I might check this one on a calculator and use a table and plug in numbers that are close to 0 on either side of x equals 0 and make sure I'm getting outputs that are close to negative 1/2 since I did a lot of work here. All right, what it did ask me to do here though is use theorems. So I've used that and I've shown work for that. The one thing I have not yet done though is cite which theorems I used at the very end. I used functions that agree at all but one point in one step there where I did the cancellation, but at the end I used some substitution shortcut theorems, and this one is a little bit more complicated because of the radical. So just like problem 12 that we did before, I actually used the substitution shortcut theorem for polynomials to handle the 1 plus x that's inside the radical. I then used the theorem about combining functions and powers to handle the radical part, or you can think about composition as well. And then you might think about rational functions, substitution shortcut theorem for rational functions, but this is not actually a rational function because of the radicals there. But I do have some combining function theorems that allow us to think about addition, multiplication, and the quotient rule. So the quotient rule is what allows you to do a numerator and denominator. All right, so I used quite a few theorems on this one. And sometimes for students, that's the tricky part, is being clear about what theorems you actually used. So I will ask you on some assignments to cite that. We do a lot of homework, especially in the My Math Lab homework, where you're just kind of getting the answers. But on the written work that I'll ask you to turn in, that's where you kind of want to take that a step further and be able to cite which theorems you use. All right, for this last example, you might think about, can you use a substitution shortcut theorem? And you should pretty quickly decide that the answer is no, because if you try to substitute in x equals 0, you end up with 0 on the bottom of a fraction, which is not going to work. So you might think about what else you could do. So the next thing I might think about is whether I can do some sort of simplification. So we did a lot of problems where there was a bunch of algebra we could do with expanding out polynomials or finding common denominators or rationalizing. But none of that is really going to work here. You might think about some trig identities, but when you investigate those are not going to really help either, because you're still going to have trig functions. So This is one where kind of my list that I had made when we started this video of strategies, I mentioned sandwich theorem. I kind of try if I have decided that these other strategies are not going to work. And you might recognize that this is a problem that is similar to some of the sandwich theorem problems that we did. All right, so what can be difficult about sandwich theorem is figuring out what functions to use to sandwich the one you're working on. All right, so for sine and cosine functions, I usually start by writing down a relationship that I know that sandwiches cosine and sine function. I'm just using theta here. So we know that cosine function is sandwiched between -1 and 1 for all values of theta. That's part of the definition of cosine. But in this problem, I don't just have cosine of theta, I have cosine of 2 over x cubed. So that inequality is true for all x except the one value of x that I cannot plug in there that would make that expression undefined. So that's for all x except 0. So remembering that this limit is asking us not really about what happens at x equals 0, but when x is close to 0, we would say, all right, that's okay, because I don't need to be at x equals 0, I just need to be close. All right, when we did some other sandwich theorem problems, at this point we just multiplied through by something. And so what you might want to multiply through by on this problem is x. You do need to be a little bit careful about that though, because depending on which side of 0 we're on, we could be multiplying through by a positive or a negative number. So there are a couple of ways to handle that, but this one is a tiny bit more complicated just because that x can be positive or negative on either side of x equals 0. So I'm going to just handle it as really two separate statements here. When x is bigger than 0, so when x is bigger than 0, I'm multiplying through by a positive value of x, and so when I multiply through that inequality by a positive value of x, I'll have negative x is less than or equal to x cosine of 2 over x cubed is less than or equal to x. So I just took the previous inequality that I had written and I multiplied through by x, and the inequalities stay facing the same direction. So I have the function I was working on and it's sandwiched between negative x and x. All right, so now I want to think about what happens when x is less than 0. So in this case, x is going to be negative. So I'm going to multiply through by x again, and so I'll have -1 times x is negative x. But remember here, since x is less than 0, the x that I'm multiplying through by is negative. So that's going to cause those inequalities to flip. So I'm going to have greater than or equal to x times cosine of 2 over x cubed, and then this one will also flip x. Okay, so in either case though, the inequalities are different, but in either case, the two functions that I have sandwiching my x cosine of 2 over x cubed function are the same functions. So this next part really needs to happen that you have the same functions on each end. So this is the sandwich part of sandwich theorem. I just have two sandwiches here. And then I need to think about the squeeze part of this theorem. So I need to think about the limit as x approaches 0 of those two sandwiching functions. So one of them is x and the other one is negative x. And for both of those, I can go ahead and substitute in x equals 0 and I get 0. And on this one I get -0, which is 0. To do that, I use substitution shortcut theorem on both of those. All right, and so because those are the same limit, that's the squeeze part of sandwich theorem. So I have to establish the sandwich, and then I have to show that those two functions both approach the same value. And so for this one, at the end, I might write one more sentence and say then the limit that we were originally looking at as x approaches 0 of x cosine of 2 over x cubed, that limit is also 0. And I need to someplace in here say that I used sandwich theorem. All right, so I used sandwich theorem. There's quite a bit of work for writing out the sandwich theorem. I've got the sandwich and the squeeze part. And then I also, on the squeeze part, I used the substitution shortcut theorem for polynomials. All right, so these problems, be sure that you can not only get the answer, but understand how to write your work adequately and justify your work and state what theorems you're using. Try some of that homework.